Hello! It's time for section 2.4, part 2, part dos, about continuous random variables. So in part 1, we learned about all these different concepts of discrete random variables, like a random variable that takes a countable number of values and has this probability mass function that, sorry, having a hard time finding my mouse. That means the probability of like P of X means the probability of X, of that value, with in the discrete case. All right, if you wanted to find the probability that X equals A, you just plug A into that function. We have this cumulative distribution function that's a less than or equal to probability. We could find the probability of different inequalities, like that X is between different things, by just adding up the appropriate values. It's kind of intuitive. Sorry, this notation's a little weird when I typed it. But finding the mean, you're just going to add up the values of X times probability of X, and so on. Okay, so we had several different things, and we did an example last time. All right, so it's not too bad. Hopefully that you've had a chance to practice it and it's sort of intuitive, all right? That just means it makes sense. So now we're going to look at the continuous case. And remember, continuous random variables are things that take an uncountable number of values in some real number interval. So like a discrete random variable could be like the number of pets you have, right? But the one example we've used a lot for continuous random variables that might be like someone's weight, right? Which, when we talk about weight, we round it, right? To make it kind of seem discrete, but it isn't. It isn't discrete, okay? So what that means is we have to do things differently. So right off the bat, one thing I want you to notice is discrete random variables use a lot of adding up, a lot of summations, and discrete random variables use a lot of integration. Okay, so when you have a continuous random variable, you have to use you're going to be using calculus for now. Okay, so you're going to just see things that kind of remind you of more calculus kinds of concepts, but it's pretty interesting. Okay, because like probability experts had to figure out a way to deal with probability when you can't like count how many things there are. Okay, so now, instead of a probability mass function, we have something called a probability density function. All right, or PDF. And that symbol is going to be little f of x. And little f of x is not like, over here it was like, in the discrete case, it was a probability of something. It is not a probability of something now. It is a curve. Okay, so let's say this is the x-axis. And there's some curve that is like little f of x. So maybe that is starting to remind you of calculus. All right. And underneath that curve is like something like a histogram. We haven't really talked about histograms yet, but I just want you to think maybe like if X were weights, if these were weights, right, of people, so then maybe like 150 pounds is here or something, right? And everybody's stacked up under there, right? You could like think of like a little bar graph. That's a histogram, like a numerical histogram. All right, everybody's stacked up under there, and underneath that is 100% of everyone. Everybody's in there. You're in there somewhere, right? Okay, so that curve, f of x, the PDF, is just kind of showing you the shape of how these things stack up, okay? But f of x on its own is not the probability of exactly the probability of a value x. Let's keep going. So if we want to find the probability that x equals a, remember in the discrete case we just plugged it in, but now, if you wanted to find the probability that x equals a, it's just going to equal 0. Oh, that's like crazy, right? So like the probability that someone weighs exactly 150 pounds, it's 0. It's impossible for you to weigh exactly 150 pounds, right? Really think about it, right? Like maybe you're really, really close to 150 pounds, but there's like infinitely many different values of weight that's really close to 150 pounds, right? So in effect, right, it's like 1 out of a million, 1 out of infinite, right? That's 0. We're going to come back and look at this in some different ways in a second. The cumulative distribution function, the nice thing about that is it still means the same thing. So if you wanted to find, if they asked you to find f of k, it's the same exact thing. Although I haven't explained how to find a less than or equal to probability yet. Okay, so let's wait on that. So you're still less than or equal to probability. So these are that has the same definition, but you don't add them up yet. So we'll come back and fill that one in too. I know we're kind of zooming through this, but helps because you'll see something. So now, if we wanted to find the probability, this one we can do, that x, some variable x, like a weight, is between two values. Like, what's the probability somebody weighs between 150 and 170 pounds? Well, we have this f of x. Whoops. It's doing it again. All right. So we have this f of x, right? Remember we had this like curve, f of x. And so whatever a is, we find that. And then we find b. And the probability is going to be the area between those. So maybe you remember how to find the area under a curve. It's an integral of that. So over here, it was like add up appropriate values of p of x. Now it's integrate across the appropriate values of f of x. They're very similar. Remember, if you remember calculus, right, an integral really was just adding up like infinitely many little things, okay? All right, so that's how you can find that. What about this one? Finding the probability x is between a and b, but not including a and b. Let's think about that. Well, how much area, remember, probability is area under a curve. How much area do those lines have at A and B? They have 0 area. Maybe I drew them kind of wide. I have kind of a wide width of my stylus pen right now, but it's exactly the same. Because those lines, those vertical lines at A and B, have no area. And remember, we said the probability of being exactly at one of these values, it's 0 anyway. All right, so now we have a different way of thinking of this. I'm going to go back up and look at the beginning of this table a little bit. Or this part. Finding the probability x equals a. I told you it's 0 kind of just using common sense. But I want you to think a couple other ways of thinking of it, right? We know that probability is area. Well, if I just put a on there, what's the area of that line? 0. So that's another way to think of it as area, as 0. And then the other way is to go, oh, I would be integrating from a to a of f of x. Right? So that would, again, give you 0. You'd like get some antiderivative, and it would be that at a minus that at a, which would be 0. Okay, so notice there's lots of ways to think about it. Similarly, capital F of x less than or equal to k is going to be whatever you get when you integrate, right? Let's look at a picture again. I know, I draw lots of pictures. Very helpful. All right, there's k. I should have drawn k over there more, but we want x to be less than or equal to k. So it's going to be whatever this area is, less than or equal to k. All right, so it's going to be f of x, where k is the top limit, right? The integral of f of x from something to k. Well, it's whatever the lowest value is. We're just going to write it as negative infinity. And notice if there is a defined lowest value, you'll put that in there. We'll talk a little bit more about that when we get to class. All right, but notice that's adding. Well, here, when it was discrete, we were adding up all the values of p of x for everything less than or equal to k. Here, we're integrating everything less than or equal to k all the way up to k. All right, so they're very similar. So if you get one of them, maybe you can get the other. All right, finding the mean instead of like adding x times, like adding all the values where you have x times p of x. Here we're going to integrate all the x's times f of x values. Dx, same kind of thing. Still a like a weighted mean, weighted value. Okay, it's getting weighted by these f of x values. So the higher the value of f of x, it's going to weigh that value x more. And we're going to just say we're going to go from negative infinity to infinity, knowing that really this is like some maximum value and this is some minimum value. And then if you want to find the variance, right, so finding the variance and standard deviation, the variance, sigma squared, is the expected value of x squared minus the mean squared. To find the expected value of x squared, it's really similar to what we did when we did the discrete case, but now instead of a sum, we're going to be doing an integral from some minimum value to a maximum value of x squared times p of x dx. Oh, shouldn't be p of x, it should be f of x. Can I make that look like an f? I don't know. Yes, f of x dx, and then subtract the mean squared. And then, once again, the standard deviation is just the square root of the variance. And then we kind of skipped finding the pth percentile earlier, but here we're going to do it. So the pth percentile is this. It's some value, so if we have f of x, it's the curve f of x. It's some value where this area is like p. All right, like 80% or something like that. Okay, so what you're going to do, we call this value the pth percentile. I think they use this symbol, maybe mu sub p. Maybe it's I can't remember. It's something like that. But if you wanted to figure out what this value is, what you would do is you would integrate from negative infinity all the way to that value, right? So the bottom, right, so this area has to equal whatever p is, written as a decimal, of f of x dx. And then you would solve for mu sub p. I think maybe you have to do that try to do that a couple times in homework. All right, so I think we're going to stop there. You'll have all the notes, and when we come to class, we'll try doing some examples. All right, but you'll want to make sure you have this entire table, we didn't do this one, filled out, okay? And you'll want to be able to understand it and kind of like, if you can almost memorize it, right, or at least understand how the two sides are related, it'll really help you out. All right, that's it. Bye-bye.